sorting here. Okay, so let's pick up where we left off. We are going to be starting the sort section, I think, today. There really is a lot happening, and I think taking it section by section will probably be best. Cool. All right.
You have to do sorting. This cannot. So normally, when you look at
I need to open up my repo. Is it in here? Yeah. So cd cata machine, and then we'll do code. I don't need this one anymore. All right. So we are ready to rumble.
at algorithms books, it often starts at sorting. I think search is just a simpler concept to understand because it's very practical, whereas sorting often gets into this weird world. And so I wanted to start at search, but now we're going to do sorting. We are going to implement 2 sorting algorithms, but one of them has to come a bit later. And so the first sorting algorithm I want to do is bubble sort. Now, normally it starts off with insertion sort, but the problem with insertion sort is the example always sucks. It's like a card deck. I still don't know how to sort cards. It's always a much harder sort to start with, which I'm surprised that we start that way, because bubble sort is not only really easy to visualize exactly what's happening, it's also 3 lines of code. It's an extremely simple algorithm. Sure. And my teacher once said, Ray Babcock, he once said, if an airplane was going down, stewardess whoosh, kicks the curtain between first class and economy, because I'd be traveling in economy, and she said, quickly, we need someone that can write a sorting algorithm or this plane will crash. You could write bubble sort under a plane crashing. It is that simple. And so we're going to go over it because I just feel like it is the greatest of all sorting algorithms. And so hopefully our plane does not crash, but let's get this sorting algorithm going. So let's talk about bubble sort. So the general definition, or the the quote-unquote mathy definition of a sorted array is simply this. Any x sub I, meaning any ith position within the array, is going to be less than or equal to any I plus 1, right? Does that make sense? This is true for the entire array. That's how you know an array is sorted. So that's kind of like the mathy way of saying it. And so if we have an array that's not sorted, this property does not hold true universally. It may hold true in specific instances, but not universally. Fair. So let's start off with this array. 1, 3, I'm going to make this up as we go. 4, 2. I always wanted to memorize all these great examples, so when I did it, I could produce the best outcome, but I can never remember the example I'm going to do, so we're just going to make it up on the spot. So how bubble sort works is that it starts in the 0th position, and it's going to go to the end of the array. And what it's going to do is it's going to say, hey, person next to me, the +1 next to me, if I'm larger than you, we swap positions. That's the entirety of the algorithm. Boom, we've just done it. We're pretty good. So what happens? Let's actually go through it and see what happens. So 1 goes to 3. Am I larger than you? I'm not. All right. So then we go here. Hey, 3, am I larger than 7? I'm not. Hey, 7, are you larger than 4? You are. Well, fantastic. I'm going to put 4 here. We're going to put 7 here. Hey, 7, are you larger than 2? Oh, you are. Fantastic. So what happened to our array by the end of this? By a singular iteration, what happens in bubble sort?
It got mutated twice.
The largest item is where in the array? It's at the end. So a singular iteration will always produce the largest item in the last spot.
Oh.
So this is actually kind of unique, right?
Okay, so that's important to know. What will a single iteration of a bubble sort algorithm always produce? The largest number at the end of the array. Okay.
So that means the next time we do the bubble sort,
maybe
the
not,
Facebook as well. The next time we do bubble sort, it means we only have to go up 2, but not include the last position, because that is already sorted. We don't need to look there. So if I rewrite my array, 1, 3, 4, 2, 7. Now let's do bubble sort again, except for we only need to do it right here. So again, 1 says to 3, am I larger than you? No. 3 says to 4, am I larger than you? No. 4 says to 2, am I larger than you? Yes, I am. Let's swap. Awesome. And so, whoopsies, I just rewrote that same number.
Okay.
Again, we're done. The next largest value is in position, and we have a portion of the array that's sorted and a portion of the array that is not sorted.
Yeah.
So let's rewrite it again. 3, 2, 4, 7. And of course, now we're just down to this. So we rewalk this next progressively smaller iteration Do it again. It's going to end with a 3 right here. 2, 1. I accidentally had my entire array sorted at this point. But we would keep running until we have only one position left. Because when you have one position left, is your array sorted? It's always sorted. An array of one element is always sorted. So there we go. We did this. Now, let's kind of abstract this because we also need to figure out the running time of this algorithm. Because this is kind of a unique algorithm, right? The first time we do it, we do effectively n checks, right?
Yeah.
We have to go over the entirety of the array.
Oh, am I?
The second time we do it, well,
I thought I changed that.
All of them, right? We can do n minus 1 checks, effectively.
Yeah.
Well, then the next time we don't have to do it again. And then, of course, we keep on doing this.
How you doing?
Until effectively we reach this point.
How are things? I will be doing PoE later on, though.
We are now down to the very
right now, I'm just doing some nerdy stuff before I do more nerdy stuff.
Right away, right? This is a very familiar pattern that you should probably be familiar with. For those that don't know about this, there's a fun little story, and I'm going to say it now. Sorry that it does contain a curse word, Mark. Hopefully you'll forgive me. But effectively, there's this asshole in 3rd grade named Gauss, and he was known as being a complete jerk. And his teacher, very frustrated with all the kids, one day said, "Kids, that's it. Everyone sit down. I want you to add numbers from 1 to 100.
We're learning Gauss sums.
Did it in about 10 seconds. He was completely done right away, went up and showed his teacher. His teacher said, "No way, this is not true." And of course, it was true. And this is what he showed her, is that if you think about it, this is 101. You just add those two numbers. Well, what do you have left? Well, you have 2 to 99. All right, well, let's add those two numbers. What do you have? 101. You can kind of tell where this is going. It's going to keep going until you have 50 and 51, right?
101.
Awesome. So really, if you think about it, you could just do 101 times 50, and you have the answer. But of course, we're computer scientists. We abstract this formula. So what do? Well, 101, and this was 100. I mean, to me, that's n plus 1, right?
True.
50. Well, you know what that looks like? That looks
n
like
over
n
2
divided by 2. And if you run this and you do it, it works every single time. N times n plus 1 all over 2 just will tell you the sum of numbers between a range. And so the reason why I make that, or I say that story, is my math teacher told me that story, then went on to tell all the reasons why Gauss was such a jerk. But he was also extremely smart. I think his middle name was Friedrich. Anyways, fun story. But this always stuck with me because of that story.
Yes.
I always remembered it because now I have it locked away in my head. And if you look at this, if we just reverse that, you know what we'd have? 1, 2, 3, all the way up to n, right? We now know the formula, which means we have n plus 1, n over 2. Let's break it all down, do the whole mathy thing. Well, first thing we can do is we can just drop constants, right? Because this is, of course, big O. We're not concerned about constants. So that means it's n squared plus n, right? Well, in big O land, a thing you will do is drop non-significant values, meaning this right here. I believe the term is actually insignificant values. There we go. It's n squared. So that is the running time of this algorithm, is it's n squared.
Embrace being a nerd.
And,
embrace it.
The reason why you drop this is just imagine the input.
Oh, of n squared, I see.
10,000, right? N's 10,000. N squared is like, I don't even know what that value would be, 100 million, I think, off the top of my head. But either way, that's a very large, like, it's so insignificant at some point, it just eventually goes to 0. As n goes up, insignificant polynomials go down.
Yes, welcome to the math side. Okay. So, what is the time complexity of bubble sort? It's O of n squared. But the thing is, I think I can just do this. I can just do that. Nice.
So there you go.
So do I really? I kind of do. It's kind of important. I'll do this. It's n squared. Nope. Plus n, which then becomes that. O of n squared. Cool. LOL. BRB. Need more popcorn. Go get your popping corn.
That is the running time of bubble sort. And I'm very thankful that a 3rd grader who makes me feel stupid actually was able to solve this for me, because now I have the value right here. And of course, you know what we can do? Well, we can implement this. And I think we should implement it because it's so dang simple.
In
and
TypeScript.
It'll also be your first sorting algorithm, which anyone doing an algorithms class has to at least implement one sorting algorithm. So I do expect everyone to open up their editor immediately.
All right, I'm doing it. I'm doing it.
But let's look up bubble sort. up and up bubble sort, and it comes with an array.
Okay, so wait. I think last time we had it this way, and this was this way. But I'm looking for bubble sort. Okay, bubble sort.
And it's, of course, a sort in place algorithm. So hopefully everyone can do this, follow along. So again, remember our algorithm.
Okay, first we'll watch it the first time.
Ideas in our head into code.
And then we'll go
what
through.
I'm going to do is I'm going to create another one of these, and let's just kind of think about it in the abstract terms. We have an array from 0 to n, and we need to start at 0 and go up to, but not including n or n minus 1, because, of course, we're going to take I and compare it to I plus 1. So we don't want to go off the array. If we are using a more traditional language and you went off the array, what happens? Array out of bounds exception if you're in Java. That's, I think, what I had the program is. If you're in C++, you hack yourself. I don't know what happens, but things happen if you go off the array. So we don't want to do that. I don't want to be reading HTML. I hear that's the hacker's language. And so what we want to do is go up to this. We want to go up to, but not including
I said HTML.
n minus 1. OK, so that seems pretty easy, right? So we're going to go for I up to, say, n, right? That's our thing. We need to do this n times, right? We got to keep on bringing that number down until it's 0. And that means our inner loop needs to be the one that's actually going to be doing the special magic and doing all that. So it needs to go up to n minus 1. But remember, every single time we do a loop, the last item becomes sorted. So we can also minus I. Does that make sense?
Indeed.
We keep getting progressively smaller as we go. For the 0th case, we go up to n minus 1.
Indeed.
For the first case, we go to n minus 2. For the second case, we go to n minus 3, etc., etc. And from that point, the only thing we have to do is do a simple comparison, right? If the array I is greater than array j, swap, right?
Indeed.
I and j. That's really all we have to do.
Right?
That's the extent of the algorithm. It's an extremely simple algorithm. There we go. Obviously, when we write this out, this will be a little bit bigger.
True.
All right, so let's just write that thing out. We have the idea in our head.
All right,
so of course, we always do, I'm positive all the JavaScript people aren't used to writing out for loops, raw for loops. I think I've seen it called on Twitter. But, this is just what you got to do in the real world, You got to write these for loops. So let's go here. Let's do an I and the j loop. Awesome, so hopefully everyone has that. Now we need to do something with the j loop. Remember, we got to go up to.
Did he just?
But not include. Awesome, so hopefully everyone has the real world, You got to write these for loops. So let's go here. Let's do an I and the j loop. Awesome, so hopefully everyone has that.
Okay, so he did something where it just
something with the jth loop.
redid the action.
We got to go up to, but not include also the last element, the first iteration, because we're going to do a +1. Remember that. So let's -1. Then remember, every single time we execute, the last element becomes the largest element. We don't need to redo that, so we're also going to minus I. So that makes sense. There we go. We've now translated this code into this code. It's just a little bit more mechanical, not too bad.
Fair enough.
If array j is greater than array j plus 1, well, now we need to swap. Swapping, always not all that bad. Const temp equals array j. Whatever your first line is, you just repeat array j equals array j plus 1. Copy that and go to array j plus 1 temp. There you go. Simple swap, right? I should have just created a function that anyone could use. I don't know why I didn't. You just have to write it yourself. There we go. And now this should be effectively bubble sort. So I jump back here, npx jest bubble.
Let's see. Does it work for him?
Bubble A. That would have been so much.
Okay, it passes. So let's try to implement it ourselves. So we have a for loop. So it's going to be for when I is equal to 0, I is less than r.length. And then he does ++ I. So for the sake of keeping in the same, he did this, then shift v2 down, yank, paste, right? fi rj, and then he did something where it did it automatically for him, but I'm not sure how he did it. So he said here it's r.length -1 minus I, so that we can continue shortening the length of the array. And then he said let temp or const temp is equal to rj. Oh, undo this line because we are going to need to do a check. If rj, and I think he said it's greater than, right? Because if it is greater than, then we need to do the swap. So it's rj plus 1. he says here it's going to be const temp is equal to array j. Oop. And then array j is equal to array of j plus 1. And then, whoa. Don't do that. Plus 1 is equal to, okay. And then I think we can just run this, right? So he says npx just bubble. Hey, it works. Nice. Okay. Raw dogging those loops, dude. I am. I'm going to take the dog out again. Be back in a minute. Okay. Sounds good.
If I should have called the file Michael Bublé. That would have been great. There we go. And so now we've just written bubble sort. It's really not all that hard. This is an extremely simple algorithm to be able to do. You should just be able to do this first try for the most part. I mean, I just did it first try, so everyone can do it first try, right? But it's, I mean, if you really think about it, it's actually a very concrete, simple algorithm. It's probably simpler than binary search. In all technical perspective, binary search is significantly harder than this array or than this sorting problem. We did it. Awesome. Your first sorting algorithm. How does it feel? Is everyone pretty excited about their first sorting algorithm? I'm excited. All right, there are other sorting strategies I want to talk about. But sorting
recall how to do binary search. I believe so. I think we might have to. Hey, Carzy, how's it going? Yeah, front-end masters. I'm trying to do some DSA. Just running through it and then uploading it on YouTube. But I was paused here for a moment because I was thinking about the last time we did this, and I'm trying to recall the binary search algorithm where you need to find the midpoint and then you have a conditional, right? And you double check to see if the midpoint is equal to the value. Otherwise, you need to double check and see if the midpoint is higher or lower than the value that you are looking for, and then adjust. Oh, hey, thank you for the subscription, Carzy. Thank you so much. Welcome to the stream. Yeah. Cool.
And I haven't recovered recursion yet. And so until I cover recursion, I don't want to go into that because I want to make sure everybody is on the same page when it comes to recursion. Because the problem with recursion is recursion, of course.
I think we can recall
really
binary search.
Completely understand it, I feel like. I felt completely lost. And then all of a sudden I felt like I understood it completely. Like there's no middle ground. It's not like, well, I sort of understand. No, it's just like you either get it or you don't. It's a very painful concept. All right.
Yeah, recursion is horrible.
Questions? I've only ever had to implement a sorting algorithm.
Of course. Thank you.
So, very, very rarely.
Since we're comparing each element of an array with another element of an array, it's kind of n square. But I just didn't understand that n into n plus 1 by 2, how did we came up to that?
So the first part of your question was we're comparing two elements of an array, so that's n squared. But how did I come up with that formula and all that? I can go over it one more time. So remember, that's why I did that very fundamental thing. When you access an array, what is the runtime of accessing an element in the array? It's that fixed computational cost. So it's O of 1, right? Every time you access is O of 1. So if we access an array twice, it's just 2 constant, right? So this is all constant operations. Everything in here is constant. So this part of our operation is constant. Nothing in there is based on input size. It's all constant. It's really just these two that cause the squared algorithm because we're going over the length of the array, and every time we go over it, we go over some or most of the array every single time. So we go over n.
Sure.
So now how does this thing, we can go back to this proof. So I'll just kind of go back to the simple version of it all. Remember, I'll just kind of re-explain it just because the reality is we're doing nothing different than summing all the values. Because if you think about it, we're going to run n times the first time. Actually, well, technically the first time we run n minus 1 amount of iterations through the loop. If you look at the code, we're running, the very first time we were running n minus 1 amount of times. The next time we run n minus 2 because I becomes 1. We subtract that off also. The next time we run n minus 3, and we keep doing this all the way until we get to 1, right?
Yeah.
So if we sum all these numbers up, the way to be able to sum this, of course, is via that formula that I showed you. And so that's how many literal steps we're going to take. And so there you go. We could replace this technically with n minus 1, right? n minus 1 multiplied by n minus 1 plus 1, right? I did a bad job. But again, yes, there's still going to be an n squared somewhere in there, right? Like if you just use FOIL, you'll see that it n squares eventually. There you go. You have it. So the actual real running time is n squared minus n over 2. And then break that all off because insignificant factors, all that. It's still n squared.
As it approaches infinity.
So nothing really changes. I just tried to keep it pretty simple. All right. I think it's a good time to move forward, right? Oh, we got one more question.
What's a good sorting algorithm for immutable arrays? I assume all allocations for bubble would be deadly.
Well, the thing is that if you create an immutable array, you have to come to it with the fundamental understanding that you are creating an exceptionally poor performing data structure. Immutability is supposed to come with the ease of use, but it comes at the cost of space and replicating space. And so yes, computers are extremely fast at memcopy, but that means you're doing n operations over and over again. So if you were to literally do that, the worst case scenario is that you have a reverse sorted array and you try to bubble up. That means every single time you did that, you'd have to bubble, which means you'd have to copy n. So it'd be somewhere in the n cubed, if not higher. I'd have to think about that, but it'd be a very poorly performing algorithm. I also would never use immutability and sorting in the same sentence because that just seems like it's a terrible idea for performance.
Wouldn't immutability mean that you don't want it to be sorted? You just want it to be what it is?
So we're actually on to the second data structure. Is everyone filled with exuberance, joy, happiness? Okay, good. So I did say something weird earlier, of course, which is this statement in JavaScript is not an array. Now, we have a pretty solid definition and understanding of an array.
Next, you're going to say, isn't a programming language.
It's not an array, right?
I always argue that it is a programming language.
You can grow it, right? It can grow ad infinitum, right? So something's happening on top of an array minimally, right? Can we at least say that? That there may be an array underneath the hood somewhere, but somehow we have the ability to add. We have the ability to insert. We have the ability to delete from, in which all the indices are actually being adjusted. Because if I shift an array, the first element in the array becomes the 0th element. And so therefore something had to happen, because surely arrays don't offer that. If you delete the 0th element, you null it out, you zero it out, and 1 is still 1, correct? So something is happening. Something more than just an array is happening. Some sort of organizational structure around it is happening. All right. So I'm sure some of you are getting pretty offended by all this talk. Yes, I'm going to say HTML is not a programming language. NeoVim is the greatest editor. Rust is the greatest language, and Linux is the only machine you should develop on. Hot takes for everybody.
Hot takes
but
only.
Let's keep on going. We're going to go to our first real data structure. The reason why I'm calling it the first real one is because arrays just don't feel real in some sense, right? They're so raw, they almost feel like a primitive of computing, right? They don't necessarily feel like they're something. But I mean, there is a lot of things happening underneath the hood. Nonetheless, it still feels very raw. So let's keep on. Let's go. Oh, I did have this funny joke in here, which is it's available in pretty much every language except for JavaScript. Anyway, so what sucks about an array? Deletion. Well, you can't really delete, right? You can zero out something. Insertion. Well, you can't really insert. You can write. It's ungrowable. Why? Remember Fred. F's in chat for Fred because F went away. So let's talk about linked lists. Okay, so this is really our first real data structure. They often call this a node-based data structure. No, not node as in the runtime for JavaScript. Node as in the type of container that will wrap our data. So let's talk about this. This is pretty fun. This is where things I think get really fun because now we're actually getting into really the heart of the beginning, like the first ventricle, if you will, of data structures. Wow, what an analogy.
What a word. The first ventricle.
All right. So in a linked list, how you can think of it is that if you have a series of values, whoopsies, B. Oh, nice writing. What you're going to see is that you're going to see data organized in such a way that you will not only be able to visit, say, this node, it will point to the next node, which means that things like getI obviously work a lot differently, right? You can't just get the ith structure. What would you have to do? Well, if you start here, if this is our head, our first element, we literally have to go, okay, 1, 2, 3. All right, we wanted the 4th item or the 3rd index. There we go. We just got it. We can return out this value. And the reason why I draw circles around this is that it's often a containered item, meaning that you hand me a value t, and I put something around it. So that's why I call it a node-based one. So imagine you have a type definition in TypeScript, which is generic over t. What you'd see is a value, which is going to be of type t, and say a next, which could be an undefined value of another node. Oh, my goodness. So this was the first algorithm that blew my mind. You can see us allocating walking memory. I thought this was just like the coolest thing. I hope you feel the same way. This is like the coolest moment in all of my programming career that I can really tangibly remember, is being able to see this in my head and how it worked. And yes, I did see in Java at that point. Please don't make fun of me. But that's just how it was, you know. Everyone's first language is sometimes unimpressive. So there we go. So this is how a linked list fundamentally works, is that you have a node that contains a value and a reference to another value or to another node.
Okay.
And so that way you can walk this daisy chain, if you will, of nodes which contain values. So this would be considered a singly linked list. Why is it considered a singly linked list? Because A points to B, B points to C points to D. You can't walk backwards, right? The moment you go forwards, if you don't have a reference to what is behind you, you've lost it forever, right? It's gone.
True.
If I take head and just point it to here, no one's going to be able to access A, right? It's just gone, right? Hopefully, I believe JavaScript's garbage collection is so super advanced, it actually even collect A, because it can tell that though it references data that still is alive, it itself has no references left, therefore dead, right? Now, a doubly linked list usually comes with an additional property. Previous node. Which means we start getting bidirectional arrows, right? With this, we get.
So I'm going to add that. So, whoops. Let's say this is sort, and this is array. Oh, that's what the two dots mean. Okay. This one is sort, and array as well. This one is going to be sort, and linked list. Okay, so what are the properties of a singly linked list? It was value and next. Okay, what additional property does doubly linked lists have? Previous. Cool.
The bidirectional nature of a node, which means we can go from A to B and from B back to A, right? We can keep on walking back and forth because we have these links right here. You are referencing the next item. And so often they call this a container, right? Because you, the linked list owner, is going to say hand it a series of numbers. But it needs the ability to store and organize these numbers within the linked list, so it creates a container to put them into and then be able to manage it that way. Does that make sense? So instead of using an array, it uses, say, heap allocated objects and puts them. Heap allocated objects, of course, mean objects that are stored in some magical memory place, which is usually more expensive than stack. That's a terrible definition, but go with it.
Containers.
All right, so now let's talk about deletion and insertion. So one cool property about linked lists is that deletion and insertion can be very, very fast. So let's just say we wanted to insert into here f. What would we need to do to insert f? Well, remember, A points to B.
Just point to it.
So let's make A point to f. F needs to point to A. Remember, because we have a previous and a next, we're doing a double linked list. This would obviously be less operations in a singly linked list, but you get the idea. Now we have another problem. B, where does it point to? Points to A. Can't point to A. Just can't, right? We have broken off this link, but we still have this one. So B needs to point to F, and F needs to point to B.
Oh.
At this point, what has happened? We have effectively moved everything over and inserted F. But here's the cool part. What did we have to do? Well, we had to set a bunch of nexts and previousses, right? Like, that's it. Are any of those operations based on how many nodes? That makes
so much more sense now.
No. Are they constant time? Setting next, is that constant? Effectively, right, we can assume that it's constant. You could argue that in TypeScript or in JavaScript, looking up a property on a value could be this under these conditions. Let's just forget all about that and just assume that this is a more traditional style. If you set a
JavaScript sounds complicated.
Piece of memory on an object, it is constant time, right? It's an offset into the object, sets the memory, boom, boom, boom. There we go. So if we set two nexts, right, because we set A's next to be F. Oh, let me write it down here. We set A's to be F's. We set F to be B. Then we have to do the two previousses. We do B has to be set to F, and F has to be set to A. All those operations are performed constantly, right? It's just setting a property. Therefore, to insert inside of a linked list at a given position is O of 1, right? Nothing is based on input. No matter how big the value you give me, no matter how many items are in the list, None of that matters. It only matters that I have to break 4 links. And yes, those each can take some amount of time. That's why, like I said, there's always a constant. We drop the constant. It does not matter that there's a constant. Practically speaking, constants can matter, but in this case, it doesn't matter. So there we go. We actually created a doubly linked list, and we were able to insert. So let's think about being able to do the opposite. If we wanted to delete C, what would we have to do? Okay, we have C. We have C, the node. Let's pretend we got C in some constant time, or we just had access to C. So we're not considering how we got C. We have C, and we want to be able to delete it. So what we're going to have to do is the first thing we're going to need to do is we're going to go from C to B back to C and break that link, right? We don't want to do that. We now have access to B. We're going to have to break the link from B, and we're going to have to point it to C, which points to D, right? We're going to actually have to point through C's next to D, right? So we're going to have to go back, take its next, and point to my current one's next. Do you see? I know. The linked lists are terribly hard to implement, and you often get it wrong your first try, right? So if you think about that, practically speaking in more kind of code sense, if you had access to C, I'd say C previous equals B, right? B next equals C next. Does that make sense? Like what I just did there is I broke the link from B that points to C, and I now point it to D. That makes sense, right? I think that makes sense.
Would you put C next, or why not just put D?
Well, the thing is you have to first get access to D, right? So I'd first have to go like this. D equals C dot next, right? Then I could replace that with D. So that is equally valid as well. But remember, we're now using memory, and we're now playing around with these linked lists. So it does require us to be a lot more specific at all points. So hopefully that sort of makes sense. I mean, this is obviously a very hard concept the first time you see it, but you can see that these next and previouses, you have to be able to manage the links yourself, and that really is just setting where they're pointing to.
So linked list, there's no index. Like you can't.
The question was, in linked list, there's no index. Correct. There is no index. You have access to a node in which you can traverse to get to the node you desire. Now, there's ways to do fast traversal and things like that. We will get to that at some point, but in the current moment, we're just looking at it in a traditional kind of sense. Just a linked list as is, doubly linked to make it kind of obvious. Singly
or like
linked
helper
are really
functions.
easy to implement in comparison to doubly, because doubly you have to do this whole back and forth business. All right, so there we go. So we just set B to point to D, right? So now we need to have D point to B, right? So now notice that the operational order is extremely important, because if I said, hey, C dot next, you're undefined, could we ever access D again? No. D's gone. We can no longer ever access it again. So ordering of operations is extremely important. All right. So then the next thing we'd have to do is D dot previous would have to be C dot previous, right? So now C or D now points to B, right? We just did B to D, D to B. I wish I should have chosen different letters because they're so close. Bravo to Delta, Delta to Bravo. There we go. We now have them together. And so now we need to take Charlie over here. I guess, yeah, wow, DCB. They're terrible letter names here now that I think about it. All right, we're going to take Charlie here, and we can go previous equals next equals null, right? We've taken it out of the graph, right? We're deleting C out. So yes, D and B now point to each other. Therefore, C needs to be taken out and no longer point into anything. And at this point, if we want to return the value, we could just simply return, C dot value, right? So there we go. Does this make sense? I tried to kind of.
So D is equal to C dot next, and B is equal to C dot previous. B dot next is equal to D, and D dot previous is equal to C dot previous. So D. We'll have to see how this works.
Fundamental operations. This is a deletion. We can also go over it again with insertion and actually
this is a deletion
of the values. We will code this no matter what at some point, but this is the fundamental value right now, or the fundamental operation.
Might have to rewatch this video off
stream. Is everyone on the same page for the most part? Awesome. All right, so that is a linked list. So again, let's think about the running time of a deletion. Is any of the deleting part right here based on how big your input is?
No.
No. Is it based on how big the value of the node is?
No.
No, it's not based on anything. It's based on 4 links. Is 4 a variable or a constant?
Constant.
Confidence right there. Yes, it is a constant. And not only that, is setting next and previous, is that a variable length operation, or is that a constant operation? It's a constant operation, right? Because setting something to undefined requires going to the memory and setting it to undefined. Computer's super fast at going to memory. We can just assume it's a constant operation, though it's very, very complex. It's nonetheless very, very constant. And so therefore, deleting is constant time. Just like insertion is constant time. We do the same amount of operations no matter how big or small the list is.
What is the time complexity to delete or insert in a linked constant? Cool.
Awesome? Hopefully. Now, obviously, if you were really actually programming this, you'd have to put some like guards around this, like, right, if, B is real, then you do the whole next thing. If D is real, then you have to do the previous thing. But in our sweet pseudocode, I will always be dropping undefined checks and things like that, just because it's super hard to be able to write pseudocode and actually write really concrete correct code. So
I see.
Just be okay with things that are like that. Does this all make sense? Are we good with this one? So there you go. This is a linked list.
You just have to point things to each other in specific order so that you don't drop any value, is my understanding. But I hope he goes over it in a little bit more detail. We'll see.
We've already talked about this, insertion, deletion. Now, you can understand that if I were to get a value, I'd have to walk the list, right? So if I ask for the 5th value, there is no way when we have this type of structure right here to get the 5th value. I literally have to write a loop that's going to be like 0 to 5, and current equals current next, right? I'm going to have to walk it until we get to the correct value. Then I can return current's value, correct? We don't return the containing node because then we leak our containing thing, and then someone can mess with the next and previous values, and boom, our whole list sucks and you lose everything. So
we are
always,
only 4
that's
videos
more
in
implementation standpoint. But you get the idea of a containing node. It's our abstraction for ourselves, not for the outside world. And so in general, getting head or tail, all those things, they can be pretty good operations. So head and tail is a unique get, because in the sense that if our linked list implementation has a single reference, head, that points to the first item in the list, getting head can become a constant operation, no matter how big or small the list is.
Welcome back. Yeah, I had to pause there for a moment because I'm a child.
Getting tail can also be a constant
Also
operation.
Getting tail can be a
again,
constant operation.
We already have a defined pointer to that. It works every single time. All right, so deletion, of course, deletion at the front.
We are all children.
Right, the head or the tail. It's actually, again, constant operations, is it not? Because if you think about it, all you have to do is just take this and do the deletion algorithm. Take this, do the deletion algorithm. But if you get in the middle, or you delete in the middle, you have to traverse to that point. So you have a 2 operation cost, the traversal plus the deletion. So deletion from the ends can be constant, but deletion in the middle can be costly if the traversal is costly. But the deletion itself, of course, is not costly. Prepending and appending, constant time, again, because you are able to insert and just break the links from head or tail. So that's very, very fast. But insertion in the middle, it's the traversal, again, that can get you. So long.
What could be the most demanding part of a linked list? The cost of traversing to the middle node to implement to perform an action. Yeah. We'll underline this here, the cost of traversing, because that's the important part.
Fast, your insertion is fast. So this is kind of like the weakness and strength of a linked list, is that, yeah, it's a bit more complicated. Yes, it's not contiguous memory. There's a whole bunch of computer optimizations about contiguous memory, blah, 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 blah. What matters is that you are able to store these things. The list can be whatever size you want it to be, and deletion from the front or the back are extremely fast. And that is very, very important, because there's a lot of structures that you use in which you want to, say, delete the oldest item. The oldest item would be hopefully organized at the tail. Therefore, that's a constant operation. That's very, very fast. All right, so I don't think we're going to implement this just because time is running out, and I think it would take us, it's just a very heavy operation. You saw the next and all the previous's. But in general, this is kind of an interface that you will see if you use that Kata program that I built. This is effectively, I believe, the exact interface that would be used in the linked list, which is just like here. Here's all the operations you expect it to be able to do. Now program the underlying operations. All right, let's move forward because we got so many sweet things to take care of. We're going to actually start with linked list because they are the most foundational item Oh, we do have one question.
Singly linked
I believe
list.
the insertion of f after a is arbitrary. You usually will append f either at the beginning or the end of the linked list for constant time.
So the thing is that it just depends on how you're
Doubly
using
linked
the list.
list, I see.
If you insert at the beginning or the end, you have a constant time guarantee as long as you have a reference to both head and tail.
Maybe we'll find
depending
the
on which side you're
answers
inserting
online.
on. But if you don't have the reference to the node directly, it's the cost of the traversal to that node, and then it's the cost of the insertion, which is constant. So traversal is where the big thing comes into play here. You have to be able to find or get the node quickly. And there are strategies to do that, and there even is a data structure we're going to go over in which we have constant time traversal and constant time removal. So it'd be fantastic, right? We'll get there. But yes, so in general, I can't tell you how to use a linked list because you use a linked list how you want to use a linked list, but I would strongly recommend not traversing. Anytime you do an n-length algorithm, there's probably a data structure that's better at it, right? That makes usual sense. Sometimes that's as good as it gets, right? But for us, we don't have to worry about that. All right, so why did I start with linked lists? Well, they are super foundational. In fact, they're so foundational, every single linked list is a graph. Every single linked list is technically a tree. You can think of it in these kind of senses, so we will get to these other data structures later, but linked lists are like the most fundamental unit. And long as you understand how to traverse and move around in a linked list, you're going to understand all these other
Are we going to use them later on? Recursion, pathfinding base case, pathfinding
so we're going to get to
recursive
the point
case.
where we're going to run into, is this an algorithm?
Quicksort.
Or is
Oh,
this the data
okay,
structure?
we'll get to linked lists
Well,
later
it
on.
uses the data structure and then performs an algorithm on top of the data structure. So this becomes a more common theme we're going to see. So is linked list a data structure or an algorithm? Well, you could argue that the insertion is the algorithmic side of it. The actual setup is the data structure itself, right? We can make these arguments, blah, 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 blah. I'm not going to be pedantic. Call it whatever you want. I'm not going to be offended.
Let's not be pedantic.
All right, so our first data structure on top of a linked list is going to be a queue. This is one of the most common data structures I have implemented. I've implemented a queue just this year. I had to shove video down into a video decoder, and the only way to have a buffer to be able to do this and make sure you insert it in the correct order is first in, first out. And what is that? That's a queue, right? And I was using it in C too, so I felt I felt a little bit smarter than everybody else writing C linked list. It felt very good. So let's go over a queue. So we know what a linked list is now. A queue is just a specific implementation of a linked list. So let's pretend that we have a pointer to head, and we'll do the exact same setup, so that way I can say Bravo, Charlie, and Delta. Let's see, Bravo, Charlie. This is fun. I just decided to do this now. Delta, there we go. So this, of course, is our tail. This, of course, is our head.
Okay.
And so
Lowercase.
if we want to insert in a queue, well, before we go to that, a queue is simply a FIFO structure, a first in, first out. This is what the Brits call a line, right? And so they call it a queue, we call it a line. That's all it really is. So if we wish to insert into a line, what do you do at a carnival? What do you do at anything? You get into the back of the line. So just like that, if we wanted to insert, say, E, what we're going to do is we're going to have D, we're going to have our current tail point to E. Then we're going to update our tail to point to E. Does that make sense? So it would be kind of a two operation. You could imagine, I'll just write this in actual TypeScript. This dot tail, dot next equals E. Then we just go this dot tail equals E. Does that make sense? We break this link. We are now pointing to the end of the list. Awesome. This makes sense. But a popping operation, we don't pop from the tail. We pop from the head. Now also notice that I'm using a singly linked list. We don't even need a doubly linked list. We don't even need that extra computation time. We don't need that extra property storage requirement. We need very minimal amount of stuff. So a head, if we want to pop it, we do the exact same thing. We would first set head to point to B. So we're doing the reverse operation.
Yeah.
Head points to B. We'd save off a reference of head, of course, right? So we'd have some sort of const head equals the current head, right? We point head to B, and then we can just simply take the old one, remove the link, and then return out the value. Now remember, this is a node-based data structure, which means we have a container around the value that you hand the queue. So therefore, we have to do, container A dot value and return that out. So just to write it out, just to be complete, we'd go head equals head. I'm just going to write this out without using this and all that. You can imply this. You can imply const. Sure. And then I would do h dot next equals null. And then, of course, whoopsies, we wouldn't want to do that. That is the worst possible operation. We'd want to go head equals head dot next. Then set our saved off reference to null, and then just simply return out h dot value. Does that make sense? Just simply move it forward.
H is equal to head. So that's our current reference for head. Head is equal to head dot next. I see. So head points to A, so head dot next would be B. So now that's what we're, okay, and we are saying h dot next is equal to null. So then H, which pointed to our original reference, we're breaking off the chain there. That makes sense. Okay.
Return it. Yeah, see, if I did it the other way around, we'd lose the value, then, your whole queue would suck, and there you go. You lose all the values. Don't do that. All right, that's really all a queue is. It's actually shockingly simple, because what it's doing is constraining what you can do with a queue. And by constraining what it can do, what kind of performance are you getting out of queue? When you add to the end, what's the performance? Well, we don't traverse anything, right? We don't go over any sort of list. It's not based on how big of a value you give me. It's simply based on the fact that I have to set one next value to a new node, and I have to update where my tail points to. Those are two constant time operations, right? And creating a node itself is a constant time operation in the sense that, yeah, it may require me to go...
Wait, hold on a second. This dot tail dot next. This dot tail dot next is equal to E. This dot tail. Oh, okay. Dot next is, instead of it being the end, instead of it being null, what it's doing is it's setting it to the E value, and then this dot tail. I see. Okay.
Memory may require me to go out to the heap and grab memory, but we consider those kind of constant.
I see
time
the property. Okay, it's changing properties in the container.
Those new values elsewhere.
Okay. When I think about it that way, it makes sense.
Popping from a queue is the exact same thing, but just in reverse. It's constant. And so, fantastic. We now have reduced what we can do, and we've made sure that it's very, very fast, and it performs a specific algorithm. First in, first out. It's that simple.
Typo.
Right? It's that simple. And so, of course, there's also usually one other operation that comes with queues often, which is peek, the ability to see what is my first element without popping it off. Of course, that would just be, hey, head.value. Right? That's pretty much as straightforward as it gets. And so, of course, I already said this part. We're entering into the world where we constrain things. From here on out, you'll just notice that most things are constrained intentionally, such that we get very good performance out of it. You can only use it in a certain way. Yes, it is technically a generalized linked list underneath the hood, often with a queue, but you can only use it in a certain way.
A generalized
This one's a great one to implement. I think it's fantastic. So we can jump back over to our editor. Remember, if you do have VS Code, I do have a get ignore for everything that starts with a day and some number. So therefore, make sure that you show get ignored files so you can be able to see day one. And we can go down to queue, open it up, and look at this. It's a poorly formatted file. But there you go. We have a class that's generic over T. It has a length that has a number. We have availability for constructor. We have enqueue. So this is typically the phrase that is used when implementing a queue, is to enqueue something is to add it to the queue or push it to the queue. And then we have dequeue, spelled without two UEs, which is always kind of mind-boggling to me. But that one is to remove it from the queue. And, of course, peek. So let's figure out first our constructor, and then we can figure out the other methods. So let's actually first get our type in here. So we're going to have a little type queue node. I believe type node is a reserved word, if I'm not mistaken. We'll have a queue node that is, say, generic over T.
Okay.
And we want a value that is T, right?
Sure.
And then, of course, we're going to want a next that may or may not exist, right? We don't know how many elements we have. We can't say it always exists. If it always did exist, you'd create one of them, and you'd infinitely create memory forever and eventually blow up your system. So there has to be an optional pointer to this.
I see.
And we go queue node. I can't remember if node is taken. Is node taken? I think it... Okay, cool. At one point, you couldn't create node. It would actually fail on you. I don't know what's changed or why it's changed, but there we go. Awesome. We have type node. It has a value.
So now this is singly linked.
Itself. And so that means we can have a private head that's going to be a node T. Great, right? We've now created
private in TypeScript.
Interesting. This. And of course, this can be undefined as well, right? In TypeScript, you can always use the old question operator or whatever it's called. I forget what it's called. And then we can go tail as well. Ooh, that's teal. There we go. So now we have our two references, right? They may be undefined, but we have two references, one to head, one to tail. They're of node T, generic, or of node generic over T. Our queue is generic over T. That means we can pass in any value. We don't care what value you pass us. We create our own container, and we manage the state ourselves.
Sure.
All right, constructor. This dot head equals this dot tail equals undefined. Look at that. We're going to be super serious about this. Now, of course, length, we have nothing in there, right?
Sure.
Awesome. We've pretty much done the hardest part about a queue. Okay, not the hardest part, but one of the hardest parts, getting your constructor correctly. All right, let's start with peek, because peek is such a simple operation, right? All we have to do is return this dot head, and then, of course, do one of those little question mark values, right? There you go. That's a null operator, I believe, or null coalescing operator. I forget the exact name, but effectively says that, hey, if head is not null or not undefined, I can get the value. If it is undefined, I'll return undefined. So there we go. We now have fulfilled our interface. It's awesome. We've set it. Let's go. All right. So let's do DQ next, because I feel like DQ is not only a restaurant that serves ice cream, but also is a pretty simple operation to do.
It is.
The first thing we need to do is, do we have any? Do we even have a head? Right? If we don't have a head, we can't DQ it. So if there is no head, let's return undefined, right?
Okay.
Pretty straightforward. That makes sense to me. Awesome. After that, we need to do a couple operations. We need to do some bookkeeping. This dot length, minus minus, right? If we want the outside world to know how many items we have, we kind of need to keep track of these things ourselves.
Sure.
You're usually used to something like an array doing this for you. We are now the array, right? We are now the ones doing these operations.
Okay.
And then, of course, what is the operation? We first update head to point to the next value. Then we return out our previous head. So let's go like this. Const head equals this dot head. This dot head next equals, oopsies, wrong direction. This dot head equals this dot head dot next, right? So we saved out our head. We updated our head pointer to the next one. Whether it's undefined or not, it does not matter to us. We just updated it to the next one, and then we just got to do a little return head.value. Now, if we were using a more traditional language that doesn't have a garbage collector, we would probably want to do some cleanup here, right? You'd want to do a free here. There's things you'd have to do here that we just don't do in JavaScript. So, you know, just to be somewhat complete or make it feel as if we're doing all of our own bookkeeping, I will go head.next equals undefined. We don't need to do that, but again, just to give you the more complete feel.
Right.
Awesome. We just did DQ.
And that's the
Was
end.
DQ all that hard? No, it's really just those two simple steps. Save your head, update the head, return the value. That's two simple steps, index 0. I'm not off by 1. I'm still correct. Oh, dang it, we have to reduce our length. OK, I am off by 1 in index 0ing. So there we go. So let's do enqueue, right, which is really the opposite operation.
This dot length minus minus.
Instead of the head. So again, if there is no tail,
I see.
That means we pretty much have an empty array, right? Now, if you're using a more, if you're using a different type system, I would probably have chosen this dot length equals 0, right? Because at this point, I could say, hey, we do this operation when this length is here. But since TypeScript can't understand exactly your meaning if you don't intentionally check for null or undefines, then we're going to check intentionally for undefined. So if there is no tail, that means this dot tail equals this dot head, which equals a new node. So let's create a new node. Value is item, whoopsies, as node generic over t, right? There we go. We've now just created the node. Our next is undefined. Our value is the item. It's of type t. Our node is generic over t. Everything is good except for one thing. We don't have our length correct. So this dot length plus. Make sure you spell length correctly. There we go. This is looking pretty good, right?
So
we
this
now
dot tail
have it officially
is
done for the first or the base case.
Value
if it's
item
not
is
this,
no t.
we need to do that whole tail updatey thing. So we have to make sure we don't accidentally destroy all of our data or lose our tail pointer, right? So this dot tail dot next needs to equal the node. So let's just create out the node right now. Value, really, we could just take this. Const node equals, paste it up here, make it easy, right? And then node, I forgot that return value. There we go. Tail dot next, right here. So we've just took our tail and added a new one to the list. So now we just need to take our tail and point it to the new one, right? Right. Yes, you're absolutely correct. Thank you. There we go. Our tail now points to the last item in our list because it became the last item, and then now we are pointing it correctly. So that is all that is required to do a queue. Queues.
Okay. So let's go over what he did. He first created the node, and then he created his constructor, and he said this dot head is equal to this dot tail, which is equal to undefined, and he set the length to 0. In our peak, he just said return the value, right? In our DQ, he made it so that head pointed to in our DQ, what we did was we pointed one backwards while saving the value and then pointing tail to the previous node. And then enqueue was the little bit tougher one. What he did was he made the value. Where's this? Okay, so no, if there is no tail, this dot tail is enqueue is when you're adding. Oh, you're adding to the end. And DQ is when you're removing from the first. Okay, I see. So I had it backwards. Let's try and do this ourselves. So this was our queue. And so he said interface node t, right?
Head next head to point to the next. That makes sense. Operation to do. So there we go. We now have and okay dot head.
No, he typed not interface. Interface is Java. Type node t equals, okay, yeah. Cool. So type node t is equal to value, which is t. Is it this dot value? Oh, because key value pairs. Value is t, and next, which was, and how did we point to the next part? Node t. Huh. Okay. So it's going to be a node. If there is a next, it's going to be a node. Okay. So public length number. So in our constructor, he said this dot head is equal to this dot tail, which is equal to undefined. Right?
Equals this dot tail equals undefined. Look at that. We're going to be
This, which is equal to undefined, and then he said this dot length is equal to 0. Now, why does it not like this? Tail does not exist in type Q. Values t, next is this head and tail. Where did he? Did he? Oh, okay. In private, I see. Private head is equal to what? T. And private tail is also equal to t. T being passed through. T dot value. Node t. Okay, yeah. All right. Is this not being used? Node is declared but never used. Node or undefined. So Q node then? No, it's still not being used. Okay. So what's the issue then? Yeah. Oh, I see. It could be that I am not doing things properly. Yeah. This seems to have fixed all my issues. Node is now being used. Length is being 0. So it says here, he said this should be easy because it's return. Is it node dot value or this dot value? This dot value. No. T dot value. No. This dot head dot value. If head is undefined, then it doesn't return it. Otherwise, it returns the value. This dot head. So if it exists, return it. Otherwise, return the value. So if we're doing DQ, first we need to run a check. So if we're DQing, we're removing this dot head, right? This dot head is equal to what are we assigning it to? So if it doesn't exist, what do we assign it to?
Let's return.
Oh, we don't. We just return undefined. Okay. Oops. Return undefined. And so this dot length minus minus, right? And then he said, const head is equal to this dot head, right? And then we need to be this dot head dot next is equal to head. No, this dot head. And then we need to return, right? So this, we said, we saved the spot of it, and then we said this dot head dot next is equal to this dot head. And then what do we return? Is it just return?
Undefined, right? Pretty straightforward. That makes sense. We kind of need her now, then wrong direction. Head, just updating a more traditional language that
Had that value. Oh, I had this backwards. Okay, and then we return this dot value. Head dot value. Okay. Const head is equal to this dot head. This dot head is equal to this dot head dot next. Okay, right, because I need to set. Okay. So now we go up to this one here, and we say if no this dot tail, because this is the opposite, right? What do we do? Return undefined. That doesn't feel right. Yeah, no, that's right. Okay, so it's going to be length plus, or this dot length plus plus. And so now if we are, no, something is off here, because this is where he
keeping. I'm gonna go to this length is here, but since TypeScript can't understand exactly your meaning if you don't, which is item. Whoopsie.
Okay. So yeah, it is different. So this dot tail is equal to this dot head. So if there is no tail, then the tail is equal to the head, which is equal to the value item.
As no generic over T, right?
Okay, well, I guess we gotta fix that. This dot tail is equal to this dot head, which is equal to value of item as node of T. Right, so we are doing a type assertion as node T. Okay, so yeah, we are replacing the value. Okay. Length plus plus. So then what? Okay, so the item is being passed the value, so we're setting that the container to the value. So now that we have we're adding to the length, and then what do we need to do? So we are on queuing, so we need to pass to the opposite. So on queuing, so that means we need to, so it's this dot tail dot next is equal to this dot tail. And before I do that, I need to make sure that this dot tail is saved, right? Const tail is equal to this dot tail. No. What's happening? So with an on queue, you are adding to the end. So when you're adding to the end, you need to take the value, you need to take the next value and point it to the value. And then you need to say this dot tail is equal to this dot tail dot next. Okay, so const tail should be the value as node t, which he just said const node is equal to value item as node t. And we'll say node here, right? So let's just do this again. So we added to the length, we are adding to the end. So we need to say that the tail is equal to this dot tail. So no, temp is equal to this dot tail, right? Because we are saving the previous value. Then we need to say that the next, so tail dot next is equal to, is it this dot tail dot next? This dot tail dot next is equal to node. So we're saying that we're pointing to the next node. And then this dot tail is equal to this dot tail dot next. Right? This dot tail dot next. Is this how it goes? I just dropped my microphone. What we're saying that we have to point to the next node. And then once we point to the next node, we say this dot tail dot next, but I'm missing something.
There we go. We've now just created, we correct data destroy all of it. And next, tail now points to the last item in our list.
Okay.
List because it became the last item, and then now we are pointing it correctly.
Oh, okay. Well, I mean, it's the same thing here. I think this still works. Let's see. npx just q one failed dot to equal dq peak to equal 11. Where's that to equal?
So that is all that is required to do a queue. Queues are actually fairly simple data structures, right? They're not too hard.
Okay.
You're only managing one link. You just have to make sure you're updating or deleting that one link properly.
I need to stop dropping my mic. All right, well, let's rewrite this. So let's rewrite all of this. First, we're going to start off with typing. So we're going to say type node t is equal to this. So we have a value, which is t. And then we have a next, which is a question mark. It'll be node t. Okay. Then we have a private attribute, which is head and optional. And that's going to be node t. And then another private, which is tail. And that's going to be also a node t. Okay, so in our constructor, we have this dot head is equal to this dot tail, which is equal to undefined. And we have this dot length is equal to 0. Okay. So now that we are on queuing, we are adding to the end. So if we're adding to the end, we got to say this dot length. First, we have to adjust the size of our linked list, once we have adjusted for the size of the linked list, if there isn't a tail, right, then what do we need to do? We need to say that this dot tail, you know what? Actually, we'll do const node is equal to, we're going to update the value of the with the item, and it's going to be as part of the node t, right? So this dot tail is equal to this dot head, which is equal to node. Right? This dot tail is equal to this dot head, which is equal to node. And why is that the case? This dot tail, if there isn't one. If there isn't one, so it's the same. Okay, if there isn't one, which means there is no list, that means we are creating one, and it will be the only item in the list, so it's setting the head and the tail to be the same thing, which is the node. Okay. Otherwise, if there is, so if there is, we are on the last one. What we need to do is we need to make sure that this dot head dot next is equal to node, not head but tail, right? And then this dot tail is equal to node. Something feels off here. And what am I returning? Return this dot tail dot val. What am I missing here? So now that I've pointed the next to this, I've also pointed this dot tail to node, right? I'm not sure. I'll figure it out in a moment. All right, let's let's in here do the same thing. So in here we are going to say that if there is no head, then what are we going to do? Return undefined for the DQ, right? And if we're DQing, we take away from the length, so this dot length minus minus. So if we are taking away, so we are saying we are removing the first, so we're saying that const temp is equal to head. This dot head, right? And then this dot head is equal to this dot head dot next, right? Because we need to point it over to the next after we have saved the value. And once we have pointed it over to the next, what do we need to do? We need to say, we need to clear. So we'll return this dot head dot value. No, I don't know what we return here. I need to figure out. I need to remember what we are returning, but I'm not really sure. And this one is going to be easy. This one is just return this dot head dot value. What are we returning here?
Time to ask questions. It's a great. No, meaning I just got.
Oh, I need to go back to, I think, the previous one. Implementing a queue.
Yeah, we're gonna.
Yeah.
So let's do DQ now. Go ahead, board. Keep next value dot. Does not matter to us. If we're using a more traditional language that doesn't
Return head dot value. Head.value. What's head.value? I see. Why are we returning head.value though? And is this return tail.value? No.
Doesn't have a garbage collector, we would probably want to do some cleanup here, right? You'd want to do a free here. There's things you'd have to do here that we just don't do. We don't need to do that, but again, just to give you the more complete feel. Awesome.
Right, okay. And this is this dot head dot next. Undefined.
We just did DQ. Value. Now here, right? Free. And then we just got to do a little return head.value. Now, if we were using a more traditional language that doesn't have a garbage collector, we would probably want to do some cleanup here, right? You'd want to do a free here.
Okay.
So our value is the item. It's of type T. Our node is generic over T. Everything is good except for one thing. We don't have our length correct. Data or lose. And then node. Yes, you're absolutely correct. Thank you. There we go. Our tail now points to the last item in our list because it became the last item, and then now we are pointing it correctly. So that is all that is required to do a queue. Queues are actually fairly simple.
Are we not returning anything though? The return is up here? Okay. That's probably why I wasn't making any sense to me. Yuri, hey, welcome to the stream. Sorry. I'm trying to figure out how to implement the queue. How are you? It is very dark over here. I would turn on some lights, but it's kind of nice. It's Saturday night and I'm enjoying it being very dark right now. We're watching some front end masters. How's your night going?
Data structures, right? They're not too hard. You're only managing one link. You just have to make
I'm hacking the internet right now, okay?
Like properly.
What do you want from me? I'm trying to be the very best, like no one ever was. You're what movie writers inspire on. I am it. I've always been it. I am her.
Great time to ask questions if you don't feel like you quite get it.
Slay!
In line 6, you were saying...
Yeah. So, welcome to the stream. It's fairly quiet though today because I am going through some data structures and it's not easy trying to follow along with this. He goes very quickly. I am trying to rewrite the code. But yeah, we'll see. I'm not doing much, just staring at you. I'm hoping I'm entertaining. I think what I'm going to do here though is I'm going to copy the code and implement a queue. Implement a queue. Implement a queue. Okay, we'll just say implement a queue in TypeScript. And yank. Oh, actually, if you do it this way, copy. And then I think we'll paste it like this. Whoops. That's not very reader friendly. But also copy. And paste. You have the same mustache as the teacher. I do. You know, it's the style. Although it is getting kind of, I need to be like a true hacker. In my little hoodie, similar, like the true hacker that I am, hacking the internet. In the night, going click clack click clack. Outfit change. Let's go. If I went to the Met Gala, they wouldn't even be ready for my shenanigans. That's all I'm saying.
If there is
Oh, 6 up. Sorry, I use relative numbers. Are you saying 6 up right here?
yeah.
Yeah.
So when there is no tail, that means that is there one node or there's no node at all? Like
There's no node at all.
Yes. I'll get you as my +1, and we'll go together, and we're just going to, this is what we're going to do. We're going to start a Twitter space at the Met Gala, and we're just going to be interviewing people over on the Met Gala on a Twitter space.
All. So normally what I would do is I'd do something like this, right? This dot length, whoopsies. Oh yeah, we can do that. This dot length equals 1, meaning I just got done adding it. But of course, what happens right here? TypeScript is like, hey man, right? It can't handle that.
Okay, speaking of which, you are throwing me off because right now I want some new Crocs, Yuri. I want some new Crocs. Listen, if you think I'm not wearing my Crocs right now, you guys have me fucked up. Because look, it's always sunny in Philadelphia, bitch. Sorry, bud. I scared my cat. Sport mode for... No, right now we're still in leisure mode, Yuri, okay? I told you, listen. I only put my Crocs in sport mode when I am in a hurry. And I am in no hurry to learn DSA. Today I learned that everyone wears Crocs in the 2006 movie. Idiocracy, because the costume designer had a limited shoe budget and thought the cheap plastic shoe made by then startup company were futuristic, yet too stupid to ever become popular in real life. I'll have to watch that one later. The origin of Crocs. That is my villain origin story. Where are your Crocs, Yuri? I need to see a picture.
So therefore, I have to
You can't tell me you have yellow Crocs and then not have yellow Crocs, Yuri. I'm going to be upset.
do that.
Otherwise, we're going to have to start the Get Yuri Crocs fund.
And dequeuing, of course. There's one thing I didn't technically do here correctly, which is what about the tail, right? What happens when we remove this? Really, what you should be having is if
I got to go back to
length
hacking. Sorry,
is
master.
0, then this dot tail should equal
Beige. Like this. I need to edit this out of the video. Is this you? Is this you? Is this you? Cayman beige?
undefined, right? We need to make sure that we forget about
5th one, first row. 1, 2, this one right here. Set. Oh, they're not in English. Oh, okay. What happened here? Where'd it go? The article is no longer available. Do you have limited edition beige Crocs, Yuri? Is that what's going on? I always listen. It gets very cold here in Canada, and I really wanted some like lined up Crocs so I can wear them during the winter. But my concern is this getting wet in the snow. This is also a very much needed break during my during my studying, so I will just edit this out later on. I didn't know there were limited edition. I would be wearing my dog to step on poop. Bro, limited edition poop brown Crocs. I need to get some of those little, like, what are they called? Gibbets? To put onto, like, my Crocs. You know? Only brings up the value. It's called style, dude. Look it up. When I put these on and then I step and I'm going hunting at 4, but I have to be at the Met Gala at 5. If I ever actually wore these to a hike, I don't know if I could keep anyone off me. The heck is style? I'm not familiar with this word. Style is whatever you want it to be. Have you seen the Croc heels? I'd wear those to the Met Gala. I have seen the Croc heels. These guys? 100%. These ones right here? Yeah. Also, yes. But these ones, the pink ones, of course. Yes, this one, these ones. These ones, though, you can catch me in those. Oh, yeah, buddy. I feel like this breaks some form of TOS. Oh, they come in yellow, too. Yo! Balenciaga Croc high heels. Actually, this is actually listen, the Met Gala won't even know what hit it. Okay? You show up with this froggy on your foot. Do they even know? Do they even know? Oh man, and only Crocs. You know, I am a web developer. I can create only Crocs. You know, if you wore these around me, I don't know if I can. Oh. Where's Waldo Crocs? Dude. Anyways. I didn't want to say it. I didn't want to say it, but yes. Yes. Those are definitely dominatrix Crocs. Might as well be designer Crocs. No. Wrong word. Wrong word. We started with the D. Oh my god. In sports mode too. Oh, buddy. Okay. All right. All right. We have. Whew, it's getting a little bit. Oh man. I can't. This is hilarious. We have about 20 more minutes left. It's getting croc in here, so I literally just put on my clothes so I can be the ultimate hacker. Now when my roommate turns off the light. Just keep the Crocs on. Listen, that's gonna cost you an extra $20. Crocs and socks. Oh, I am actually wearing Crocs and socks right now. This is correct. I can't actually tie a knot right now. What's happening? Bro. There we go. All right, now I'm ready to hack the internet. Time to whip out the biddies for some Croc shots. Only Crocs. jamilsino.ca/only Crocs. I'm going to create a new page on my website portfolio. I'm not going to link it because it's only going to be for those who are going to know that it's only Crocs. So you have to manually input my website /only Crocs, and then you will see a picture of me in Crocs and socks. You know, that's going to be another Easter egg. Listen, I need to see. So there is an Easter egg right now on my website. I'm going to have to hide the URL somehow, but if you go there, you will find here picture of a cat somewhere on my website. Who knows where? Sneak peek. Show the dogs in socks right now. Show them dogs in socks right now. Listen. You're not getting any free content, okay? You got to go searching for it. Everything here requires some form of payment. All right. So where were we? Back to our video. While we learn data structures and algorithms, so we can learn to hack the internet later on. We are only 7 hours away.
About it at all points in time. So little implementation detail, but so then this thing of course falls apart. It's like, hey, I can't do it. So I didn't want to just be encumbered by TypeScript types, or really TypeScript just actually technically doing the right thing. There we go. And so for that, I just go not this.tail. There you go. Awesome. It's the exact same check, right? Long as we've kept everything in nice bookkeeping order, this should all work out.
Could you clarify the peek method?
Oh, the peek method, yeah. So the peek method is very, very simple. So right now, if we just take this as our linked list right here, and we wanted to peek into our list, meaning we want to see the next value returned without mutating the state of the queue, all we're going to do is go to our head and get the value out of the head. In other words, we need to be able to get that generic T value out because the implementer or the instantiator of the queue does not care.
What
about
is my site
how the
URL?
queue is bookkept.
That is
It
a
only
great
cares about
question.
The values that it puts in and gets out. And so we do that by
You
doing
can
this right
visit
here.
my
We
website
go to our
through this
head.
URL.
If it does exist, we get the value out. If it doesn't exist, we return undefined.
Ta-da-ta-da! Pew!
Sorry, why are we setting this.tail.next to the new node itself?
All right, so yeah, so right here. So let's go over that operation. So that is an insertion at the end. So let's actually just do that again.
Yes, sir.
So if we wanted to insert f into here, we have to do two operations. We first have to go to the tail and set its next to point to f.
Correct.
After that, our tail will still be pointing at e, which is not our true tail, right?
No.
It has to point to f. So we also have to update tail to point to f.
Absolutely.
So if you look at the code,
Let's
exact
hack.
same thing. We go to tail,
Elite
and we set
Hacksaw.
the next one after the tail, then catch the tail up. Because the tail should always represent the end of the queue.
You can't hear it
this
right
look
now,
good?
but I'm clicking and clacking
Awesome.
on my keyboard.
All right. So what's the opposite of a queue?
What is the opposite of a queue?
Stack. I know.
Hey!
Obvious. Very, very, very obvious. Oddly enough, I've also created a lot of these things. These things are great for performance. Technically, with JavaScript arrays, awesome to use. You can use push and pop at pretty much constant time rates. Good times.
I want this to be
let's talk
over
about it.
soon.
Let's go over. Let's see how this thing works. And of course, we're going to be using none other than our beautiful linked lists right here. So I'm going to create another one of these.
What I'm probably
So,
going to do
for
is
those
just
that
do a
don't
little bit of
remember,
Astro work
a linked
after this.
list is a node.
Just finish
like
off with some
algorithm,
coding
which
stuff.
is going to have a value, which is going to be a t, and then it's going to have a next, and sometimes it will also have a previous.
Absolutely.
If it's a doubly linked list. And of course, these are of type node t. All right, so now that we kind of back into it, so if you can think about it, here, I'm going to redraw our nice little list here, A, B, C, D. A stack is a lot like, so this is a queue, really. This is actually how you do a queue, right? You have your head, you have your tail. Now, a stack is going to be backwards to a queue. So what we're going to do is we're going to actually have A points to B, points to C, which points to D. And what we're going to have is this is going to be our head. So it's as if
it's
we
backwards.
pushed in A, we pushed in B, we pushed in C, we pushed in D. Now, the reason why you have to draw it backwards, I always draw it backwards because it's so much easier to draw it backwards, is you really kind of can think about this like a stack of plates. If you have an error in your code, you get a stack trace. You want to guess what a stack trace is? It's the stack of functions that you have called up until this point. So a stack is something which looks like a queue or acts like a queue. It's a singly linked list in which you only add and remove from the head. That is why the arrows
I need you guys
backwards,
to know
or at
that
least that's
this
how I always visualize it in my head. You
this
don't have
frame
to
is
draw
a
it
metal
backwards.
frame,
Just
and
for
it's
me, a
currently
lot
digging
easier.
into my
so
nose.
if we were to add to a stack, we would do the exact same thing. We would take heads
It's
next,
being a bit
or we'd
nosy.
take E, and we'd point to head. then we'd update head to point to E. Right? So instead of doing it the Q way, which is slightly different, we point E to head. We update head to point to E. Pretty simple, right? We do those operations backwards.
Whenever I learn data structures and algorithms, this is going to be my outfit from here on out.
You'll also leak it, and then you now have more memory floating around. The reverse operation of a stack, of course, is removing it. So what would you do? If your head was pointed right here, you'd update your head, or first you'd save off this, then you'd update your head to point to next,
sure,
or previous, depending on how you want to create it, and then you could return out E. E would no longer be pointing here. We'd break it off from the graph. We just do the opposite in reverse. So it's a lot like a queue. In fact, it's so much like a queue, it's very, very easy to get them confused and or accidentally program them one or the other way, and even more so when drawing them, get your arrows backwards, right?
I see.
So a stack is also very, very simple, very, very easy to use, and you use
last
them all
in,
over the
first
place.
out.
The big thing that you'll definitely see them with
in, first
is
out. Oh, okay, yeah.
coming up here when we start doing recursion, it's really good to think of calling functions like a stack. Once you start looking at the world like a stack as you call functions, it becomes easier. And we'll go over this in more detail when we get there, but it just helps give you a mental model of what's going on actually within the computer. Because when you do call a function, it is actually
who has the better mustache?
Something
Me
like a stack. In fact, the memory that it uses
or
is
Prime?
called the stack for a reason, because it is only going up and down. There you go.
So it's kind of hard to tell.
So
it's like almost like the exact same mustache.
Exact same thing as a queue, right? Take the head. If there is a value, we return the value. Else we don't return anything. And again, constraints. They're awesome, right? By only allowing pushing and popping from one side, we can make them a really fast operation. Because what is the operation, again, for updating pointers? Constant. It doesn't matter how many items are on the list. It does not matter how big the value is. The fact is we are just simply setting things to null or setting them to point to different values. We kind of consider those constant time operations. Again, I know property access on an object in JavaScript may or may not be constant time, blah, 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 blah. We just don't think of it like that. All right. Though I did have an interview once at Uber in which the person made me not only go over all the runtime, they're like, well, you didn't know that, accessing properties in JavaScript is log n. And it's like, oh, okay. Then if that's the case, then everything just put a log n on the end of everything. He's like, well, then what's the runtime time? I'm like, well, you just put log. And it was just like the longest, most drawn out, make everything, add the word log n to everything. It was very annoying. So
that sounds annoying.
We just don't do that. All right.
Okay, so I think this is going to be the last thing that I watch before I move over from this.
Go back to day one. If you're using
move on from this because I'm going to start working on some stuff.
Get ignored folders being displayed. All right, so let's go to stack and let's implement a stack. I have everything generated to which we should be able to kind of do this all. And so I'm going to do something a little bit different when we define the node. I'm going to go type node, generic over t. Oops, forgot to do that. So we're going to create our type definition of the node. I always like to start here because what does our data actually look like? Well, of course, we're going to have our value, which is the generic value over t.
Yeah.
And then I'm going to do previous instead of next. The reason why I do that is it just makes it a lot easier for me to visualize.
Okay, so now that my roommate has turned off the light,
I draw the arrows backwards. It helps me remember
hacker.
Where I'm adding to. It just makes it a little bit easier. Again, we don't return this container to the outside world. Nobody else uses it. So you can represent it the way that is most convenient for you. For me, previous, always the bestest. All right, so just like before, we need to define where our head is. So I'll go private, head, node, t, and of course it can be undefined, correct? So if it can be undefined, put the little question mark operator. Awesome. Hi. And then now we can go to our constructor, set our head to undefined, because I just really like.
One sec.
Hi, bud. Oh my goodness, hello. Hi. What? Oh my. Hello. Hi, puppy. Oh, don't lick my face. Oh, don't lick my face. Hi. Hi, buddy. How are you? Oh my goodness, hello. Hi. Yeah, I haven't seen you all day. How are you? Okay, let's go back to this. Hi, buddy.
Being explicit, and let's go to length equals 0. So we have our constructor done.
You want to come? What do you want? What do you want? What do you want? Come here. Hi, puppy. Okay, let's watch.
Again, one of the harder parts, make sure you have everything all set up. Everything's good to go. And let's start with peek. Peek is kind of a very simple operation. What is at the head? Okay, so we can return this dot head value.
Doggo!
So if we have a head,
hey, Doggo,
we return the value. If we don't have a head, we return undefined. Peek. Awesome. All right. let's start with push. So typically in a queue, you do enqueue, dequeue. For a stack, you typically do push and pop. JavaScript chose shift, unshift for queue-like operations. Really unfortunate. I always like to pretend that when Brendan Eich was building a queue and they said, hey, how do we take this thing off? He's like, you shift it off. And they're like, oh, yeah. What happens if you want to push it on? He goes,
Are you done?
Unshift. And then that's how he got it. He didn't know, and that's how it ended up.
All right. Yeah, 1 second. There we go. Oh. Yep.
Yep. Boy, it's so good.
All right. Whew. It is getting warm in my outfit, though. It's not easy being an elite hacker. How do people do this? Yeah.
Happy. That's how I like to, do it in my head. I don't know if anyone actually really believes me on that one, but I believe in myself on that one. All right, so if this dot head is undefined, well, all we need to do is just set our head to the node, and we're good, right?
Sure.
Pretty straightforward, I'd say. So let's go like this. This dot head.
Oh, dude. I was actually just thirsty. I'll drink one for you. Cheers, man.
Equals, actually, let's just create the node outside here, because remember, we're going to need to use it in multiple places. Value is the item, and then, of course, as node, or else TypeScript's going to be like, that's not a node. So there we go. We create that. Head is node, and we return. Simplest case right there. But of course, bookkeeping is always important when using a stack. So this dot length plus plus. Let's make sure we alter our length, set our head if there's no head. Now, if there is a head, what do we have to do? We have to do the exact same operations we did right here. We're going to have to take this. Let's just add an F right now, right?
Yeah.
So what we'd have to do is we'd have to take our head, and we'd have to point to it with our new node. Then we take our head, and we point to the new node. Two-step operation. Should be pretty straightforward to do. So let's take our head, or let's take our node, and let's point to it, right? Point to the head. There we go. First step done. F is now pointing to E. Now let's make the head point to F. So this dot head equals node. There we go. That is the
push. You are adding to the end of the queue, or of the stack, right? So when you're adding to the end of the stack, you make the previous, the previous end, the head of the new node, and then, I see. Cool.
The entirety of pushing in a stack, I think it's pretty dang easy. Hopefully everyone feels good about that. Now pop, well, it's pop. So let's do this right here. So the first thing we want to do
if there isn't anything, return undefined.
Have anything to actually get out. So let's go this dot length. Let's do our bookkeeping, of course. Ooh, we don't want to do our bookkeeping quite this way. We can't just simply decrement our length, because we'll go into -1 territory if you keep on popping. So we do have to be at least a little bit smart about this, right? Equals math.max 0, this dot length -1, right? So that way we always stay at 0, or we count down.
Or we decrement.
Pretty useful. There we go. So at this point, we have to make a decision. If this dot length equals 0, well, we can go this dot head equals undefined, right? Because we no longer need to have our head anymore. We want it to be completely disconnected from our kind of container. Therefore, JavaScript will clean it up. Everything's good. But of course, we need to save out that value, right? Head equals this dot head, and return head dot value, right? We can kind of do this. But
so what happened? So I said this dot head is equal to undefined, and const head is equal to this dot head. Oh, okay. I see. Okay. This is because we have removed something, and we need to return the value. Okay. All right.
And TypeScript does not like this type of programming. Even though we understand what is happening here, TypeScript hates it. So this time, instead of doing it that other way, I'm going to do it like this. Because I don't know.
And who is this person?
This works out, right? We know what we're getting ourselves into. All right. If that's not the case, well, then we need to actually detach the head. So let's go over that operation one more time. If we were to detach F, what do we do? Well, the first thing we want to do, save out a pointer to F, so we can now access it. Second, update head to repoint back to the previous one. Third, return the value that's contained within F. So let's do that right now. We're going to jump in here. We saved out the value that is pointing to F, right? So here's F, if you will, in this category, or in this case. Then we need to go this dot head equals this dot head dot previous. Of course, TypeScript, again, still battling us, going, hey, are you sure you want to do this? So we can actually just use our actual head reference right here. Right? That also works if you want to get rid of it. We're already pointing to it.
Have you gotten
Awesome.
used to programming with
And then
Vim
lastly,
/
we just simply need the
TreeStrokes?
return out,
Sort of.
head.value.
So
again, this is JavaScript. There is details in which it's hiding from you. In languages you manage your own memory. Remember, we're still pointing to the list.
Habits that I'm learning so far are bad, and I'm trying to update
so in more
those.
traditional languages, you would definitely have to free this item. If you're using Rust, you wouldn't program a linked list because it's too hard. If you're using C++, you'd have to free it. All right. It's a good joke. There's a joke somewhere in there. It's pretty good. And I believe this is pretty much everything we have to do to...
Okay, well, let's try this again then. So now, ours, I am going to queue, bubble sort, oops, save, right? And what am I going to do here? Bubble sort and queue. Sure. I don't know what I did with the bubble sort. Oh yeah, the bubble sort was just like keep pushing, keep pushing, keep pushing. Okay. We're gonna close this and we're gonna look for stock. And now we're gonna try this again. So up here, so we're going to say type node t is equal to, we're gonna have a value, which is going to be t, and then we're gonna have a previous, which is going to be maybe, right? And it's going to be a node. All right. So we have a hang-in, and then we have this private head, which is going to be t, right? Private tail, which is also going to be t, and delete this. In our constructor, is going to be a little different here because he said this dot head is equal to, oh, I see. This is node. And yank. Okay. What did he say? I think he said this was going to be undefined. This dot head is undefined. And then this dot length is 0. Right? This dot head is node. Push pop. Oh, that's because he is let's see, what did he say here? This dot head is undefined and length is 0. Why does it not like that? This is my constructor. Right? This dot head is undefined. Okay, so there's something else that is wrong then. Awesome. Yeah, I'm just so what I'm gonna do with Vim is I'm trying to like teach myself proper technique because I'm also teaching myself how to learn the keyboard. So I'm just applying the same principles. So stack you can only add one way then, and there's no doubly linked list. So head is node t. This dot head is undefined. This dot length is 0. There's no tail. But what does it not like about the constructor? Private head. Oh, because I see. Oop, undo this. And it's because. Okay. So now that we are pushing, what do we do? If we are pushing, if no this dot head, because when we push, we add to the end, right? So when we push, we add to the end. So we say this dot head is equal to node t, right? This dot head is equal to what when we are pushing? Oh, the value, right? The value, which is item, not value, which is item, as node t, right? Oh, and that was before. Okay. And then return this dot head dot value. This dot head dot value. Oh. If no, this dot head is equal to node, which is this, yeah, and then return. Oh, just return. Okay. But first, we need to make sure that I take the length. So this dot length plus plus. Cool, and then return. But if there is one, what is it? So if there is one, this dot head dot next is equal to this, the value with item as node t, and previous, and then this dot head is equal to also the node. So when we say the previous is equal to the node before, and then we have to point it to the same one. And I just got 4 ads. I'll be taking AI as retaliation. Oh my god, Yuri, I'm so sorry. I should lower my ads to the minimum, but I will do that after the stream. I'm so sorry. Ad revenue. No. It's the cost that I pay. It's the price that I pay for becoming a professional hacker. So this dot head is equal to the previous node, right? This doesn't make sense. That's not right.
If there is a head, what do we have to do? We have to do the exact same. We'd have to node, and let's point to it, right? Point to the head. There we go. First step done. F is now
pointing to the head. Pointing to the head. The previous points to the head, right? And this dot head is what is equal to node. Okay.
Now pointing to E. Now let's make the head
leave it.
Point to F.
Get him coins.
So this dot head,
Jeffrey will be paying me out big
go.
bucks, like 20 bucks. And then in
hopefully everyone feels good.
In this dot head is equal to. I don't know if this works. So he's saying node is equal to this dot head. Jeffrey is going to be paying me the big bucks. Jeffrey Bezos. What is I cannot click on the keyboard today. Found your without tracking on your domain. Found your workout tracking on your domain. My workout? What's wrong with my workout tracker? What's wrong with it? Found your workout tracking on your domain. Yeah, I intentionally put my workouts on my domain. Node.previous is equal to this, and this dot head is equal to node. Why does this work? This dot head is equal to node, yeah. Okay, so now that we are popping, didn't know it was intentionally public. I'm not looking at the site from the front page from front end, so I didn't know. Okay, I see. No, there is an Easter egg, but my workouts I put up there just for people who like are interested in taking a look at my workouts and seeing what I do. So pop, if no this dot head and we're popping, then return undefined, right? But we need to first double, so this dot length is equal to math dot max because we needed to see if it was either 0 or this dot length minus minus, right? And if there is a head and we are removing it, so first what I need to do is make this dot head point to the previous. So it is, if there is one and we are removing it, so this dot head then becomes this dot head dot previous, right? And then return this dot head dot value. I need to return the value, head dot value, I think, not this. Const head is equal to this dot head as node, and then this dot head is,
of course, TypeScript again, still battling us, going, hey, are you sure you want to do this? So we can actually just use our actual head reference right here.
oh, so it's just, the check is if the length is 0, then we can't, okay. So this dot length is equal to 0. We need to return the head is setting the head to the node. This dot head is set to undefined, and then return the value. The head is this dot head as node t. This dot head as node t. Return this dot head is equal to undefined. Oh, okay, okay. So this is saving the value. This is setting the current value. And then return head dot value. And then if there is one, head is this dot head, which is the same thing as this. And then this dot head is equal to the previous. Okay, so it's going to be the same thing. So I can basically just say, would this work? Const head is equal to this dot head dot value as node t, right? This dot head as node t, not value. Okay. And so then this dot head is equal to undefined, and then return head dot value. And if it isn't, then head is already set as node t, and we'll say that this dot head is equal to head dot previous. Yeah. Okay. And I don't think I need these. And then the last one is this one here, and it's going to be return this dot head and then dot value if it's just a peak. Okay. Pop is to make sure that we are not removing past the maximum length, setting the head as the temporary value, as the temporary node. If there is no, if when it's removed and the length is 0, we set this dot head to undefined, so that's saying that there is no more, and then return the value. Otherwise, set the head to the previous node. Okay, okay. GG, you found it! This is why you are my moderator, but I hate you. You found it! You know, I sent someone on a wild goose chase and they still haven't found it. Okay, I'm gonna add this to my Enki, and then we're going to end it here. Implement a stack, and I'm gonna say Shift V, and we're gonna go all the way up and copy. And we're going to paste this as Java, copy all of this, and do the undo. Do this. But then 1, 2, I need to go up here and do all of this undos. And Shift V all the way down. Copy. I don't know what happened here, but somehow I managed to find my select all and change them to a lowercase t. So I will have to figure out how I did that. Okay. And where am I here? I'm going to pop this here. Cool. And change this to this. All right. So this is this, and then I will, okay, call it here for data structures and algorithms.
Here, right, at the very, and look at that, first try. We got it very first try.
So if I run this, it should be npx just stack. Huh? Oh, npx. It failed. T undefined. All right. I think it's because TR undefined. Is something off about my code here? Pop TR undefined. This dot length is equal to math.max 0. Head is this, right? This dot head is equal to undefined. Return head dot value. Oh. Return head dot value. I see. Cool. And we're gonna say stack commit and sync changes. That's been pushed. Okay. I'm going to turn on some music. I'm going to quickly run to the washroom because I really need to pee. And then we are going to come do some more code. Thank you so much for joining me, guys.